So record on here. So today we are looking at impulse and momentum. So it's the principle. Wait, how do you spell principle? God damn it. All right, let's just go with this one. Principle of impulse and momentum. And it's the last series of topics that we're seeing for the kinetics of particles. All right, so if we recall from Newton's second law, right, that said that the force, the sum of all forces on the body was equal to the mass times the resulting acceleration of the body, right? And this we had seen can be written as m times dv over dt like that, and this m can go inside because the mass of the body remains constant. It's not changing. So you get d times mv over dt like that. And we know that this quantity inside here is basically L, which is called the linear momentum of the particle, right? So basically another way of writing this whole expression is just saying that it's the rate of change of the linear momentum of the particle, right? So if I look at this expression and I take my dt over to the other side, what I see is that my F, the forces, the vector forces times dt are going to equal the differential, a small change in my linear momentum. So if I integrate this expression, right, I get this new expression where I'm integrating over a finite time period, right? So let's say that that's from t1 to t2. We're going f dt, right? And that is equal to integrating this. It's just the velocities at those two different points, right? So you can say that that is equal to my momentum at time 2 minus my momentum at time 1, right? And this is basically the impulse momentum expression, because we can say that this term here, this integral over here, is referred to as the impulse of the force during that time period. So this is referred to as the impulse, referring to impulse as IMP, as you're changing the conditions from time 1 to time 2, right? And that is defined as the impulse of the force F during the time interval from t1 to t2. Right? So physically, if you're looking at a particle, what this expression is saying is that the particle is traveling. It has some initial, let's say, linear momentum mv1. You end up imparting or hitting it with something. That's the impulse, right? So let's say that you hit it with something and you've got this impulse coming into the picture. So this is the impulse of 1 to 2. And as we said, that's defined as the integral of whatever the force of that impulse is over that time period, right? And that is going to result in a new motion, a new velocity of the ball, right? Where you'll see that that's equal to, let's say, all right, so this was mv1. Let's say that that is equal to mv2, and we know that this is going to be the vector sum of this linear momentum and whatever this impulse is, right? So if I draw it out, that's my mv1, that's my impulse from 1 to 2. Maybe I should never use that. Go here. right? So just to make sure that it's coming from the left-hand side, just drawing it for understanding's sake, I'll draw it as a dotted line, right? So you have mv1, and you have the impulse from 1 to 2, like that, right? So writing this expression out, what you end up with is, whatever your linear momentum is in position 1 at the time in which you impart the impulse onto your body is going to equal the final linear momentum of your body, right? So this is the big expression that we are concerned with. If we take a look at the dimensions, right, the dimensions of impulse are just force times time. So and depending upon the problem, you might have to integrate, or you could just do force times time directly if the force remains constant over that time period, right? Dimensions of impulse of a force are force times time. So you end up with Newton seconds, right? Or if you know that Newtons is kilograms meter per second squared, you can also end up with kilograms times meter over second, like that, right? Which is the same units as momentum, right? Mass times velocity. So if you look at the hard definition of what an impulsive force is, but anyways, before we move on to that, any questions with this derivation over here? Simple stuff, right?
I had a quick question.
Yes.
When you're given a problem, how do you know if you want to use the impulse equations or the other equations we did last week? Is how the problem asks you what to find, or how do you know what to use?
So when you have two bodies that are interacting and they crash with each other,
Mm-hmm.
then you might think that you might need to use impulse and conservation of momentum. And then, if not, if there's just one body that's changing position, then it's just work energy. But you're right, you're going to have to practice and figure out what kinetics you're going to apply to the problem, right? You'll have Newton's second law, you have the method of work and energy, and now you have the method of impulse and momentum. So
Okay, thank you.
how to select it is just from the practice. For the impulse and momentum side of things, when you have bodies crashing with each other, or you have something which is being hit, that's when you can intuitively know that you're looking at impulse and momentum. Good question. Good question. But no, that's an important question, right? We've looked at so many different things. Okay, so getting the definitions out of the way. So when you have a force acting on a particle during a very short time interval, that is large enough to cause a significant change in momentum. And this is going to be up to you to decide if it's significant or not. It's simple. You just have to look at the direction of travel and the direction of the force with which you're hitting with. Significant. Is called an impulsive force. All right. And when you have these impulsive forces acting, you can write your impulse momentum equation. And for this next expression, we're just saying that these impulsive forces don't change with time. Right? You have your initial linear momentum, and then you'll have your impulse that acts on your body, and this is going to equal the final linear momentum of your body. Right? So these are impulsive forces, right? Non-impulsive forces are forces for which the impulse is very, very small and can be neglected. Right? Let's take a look at an example where you might have different cases, right? So, for example, right, looking at like any of the ball sports, right? Look at baseball, look at tennis, look at cricket, right? You have the ball initially, right? Let's say that it has its momentum at a particular time, v1, right? And then whatever you're using, the bat or the racket, you come and hit it, right? Let's say you hit it with a certain impulse. So let's say that that's equal to delta F times T, like that, right? And that is going to result in, oops, Control Z. Should never do, I did Control Z when I was teaching my other class and PowerPoint crashed on me. So mental check, don't do that again. Right, it's going to move back ideally, and let's just assume that it moves back in a certain way. So you have M V2 like that, right? And here you can say that this is clearly an impulsive force. Well, delta F is the impulsive force, right? So this is the impulse contribution is real. Are there any non-impulsive forces acting on this body as it's flying through the air and it gets hit?
Wind resistance?
Sure, you can think of wind resistance as well, but suppose it's in a frictionless location, like the air is very thin. Gravity, the weight, right? So what you can say is that this is going to have its weight, and that's also going to have an impulse, right, over that time period. That contribution, we're saying, is neglected, and also it's not in the same direction. But anyways, you can say that it's really small, and you can neglect that. It's going to be very small because W as compared to F is going to be very, very small. So here you can say that this is non-impulsive force. All right, so that's the definition of impulsive forces and non-impulsive forces. All right, next thing, what we need to do is potentially look at this thing called impact. And this is the case when energy does not remain conserved. So we have impact, right? And this is when you have bodies that crash into each other, right? There is a certain amount of energy that can be lost due to the crash happening and potentially the body deforming and things like that. And that energy gets lost. So you can't use your expression for energy conservation anymore, right? So you need another expression in order to somehow quantify and figure out, all right, how do I figure out that energy that was lost? And you do this by quantifying what you can think of as the bounciness of the impact, right? That's called the coefficient of restitution. Quantify the bounciness of an impact using a quantity called the coefficient of restitution, or we also refer to it as just being COR, right? And this comes into play when you have impact, which is just basically the collision between two bodies, two particles. So, collision between two bodies, right? And we need to define another thing when we're looking at impact. That's called the line of impact, right? So this is the common normal to the surfaces that contact. So it's basically another way when you're looking at balls, you can think about it as the line that's joining the center of the ball. But again, the bodies that are getting impacted need not be perfectly circular, right? So the hard definition of it is that it's the perpendicular line to the surfaces that get contacted with each other and the tangent to that surface, right? So common normal to the surface in, when I say common, it's common to both bodies, common to surface in contact during impact. That's coming into the picture. And all this bounciness that's doing, as we said, right? So this COR, it's also referred to with the variable small e. All it does is that it accounts for the loss in kinetic energy that happens due to the deformation of the bodies as they hit each other, right? So all this is doing is accounting for a loss in your kinetic energy, or if you guys like the symbol, we were using symbol T like that. All right, so let's look at the different kinds of impacts that one could have, right? These are the direct central impact and the oblique impact, right? So down. So suppose you have two balls that come into contact with each other, right? We draw the line that joins the centers like that, right? And then you can draw a tangent line to that, right? So this is the normal line, this is your tangent line. And then in the case of direct central impact, the bodies are traveling in the same direction in which the normal is defined, right? So you have, let's say that this is body A and body B, right? So this was traveling at VA like that, and then this was traveling at, say, VB like that. This kind of impact is what's called direct central impact. Right? So it's basically the motion prior to collision for both bodies is along the line of impact. right? Or you could have the fact that they're not along the normal line, and that's called an oblique impact, right? So let's draw that out. So you have one ball, that, another ball, that over there, right? You have the centers being joined by the line of impact, and you've got your tangential direction, right? Oh, I hadn't defined it, but let's say this guy here is the line of impact. And it's the same thing here. So that's the line of impact, right? And here, all that you have is that the velocities are not along the line of impact. So this one is A. Let's say that one was traveling something like that. The B, right? So here you have this kind of impact is called oblique impact. Right, so there you have the motion of one or both bodies. So, even if one of them is traveling not along the line of impact, then you say that the collision is, that the impact is oblique. So both bodies prior to collision is on a line. No space. Of the line of impact. All right, so now let's look at the two cases. All right, so if we have direct central impact, right? So let's say, but before we move on, any questions up to this point? No? All right. So moving on. Looking at direct central impact, right? So you have, say, one ball and another ball. You have the line of impact like that, right? You know that, let's say that this ball is A, this one is B. So this is traveling with a velocity VA, and this is traveling with a smaller velocity VB, such that they hit each other, right? So VA is greater than VB. This is the case before impact, right? And then they hit each other, and then after impact, what happens? Right after. So this is right before and right after. So, and the separation is clearly exaggerated, right? Right after. So you have a line of impact, right? And you have, let's say that after impact, it's VA prime. And for this guy, it comes VB prime like that. This is after impact. All right, the first thing to note is, that, I didn't realize we were at the end of the page. The total momentum total angular momentum along the line of impact, only along the line of impact. So total momentum along line of impact, right, is always conserved. Right, and you might ask the question, why is that the case? Because there is no impulsive force that's acting over here, right? So if you go back and look at your original expressions, you end up for your impulse momentum equation, you take the impulse aspect out of things and look at this whole system, you get this conservation of linear momentum that's taking place. All right, so in this case, the way to define the coefficient of restitution, let me write it here so that you guys can visualize it easily, is basically equal to VB prime, whoops. In essence, it's the relative velocity before collision divided by the relative velocity after the, it's a relative velocity after the collision divided by the relative velocity before the collision. So you get VB prime minus VA prime over VA minus VB, and it also accounts for the sign change that might happen, that happens in the change in the relative velocity, right? B is going to, in all likelihood, start moving faster than A, right? Whereas here, A was moving faster than B. So coefficient of restitution is always positive. So you have to account for that. So you have on the numerator, after the impact, it's B minus A, whereas in the denominator, it's A minus B, right? The other way, so that's that. If we write this expression out, let me know when you guys are done with this. I have to move on to the next page.
I have a
I had a
question,
quick
Professor.
question before we moved on to the next page.
Yes.
After the impact, does the ball follow the same trajectory or it deflect at an angle?
In this particular condition, it will go in the same direction, right? Because you're having a direct central impact. So for a direct central impact, the directions of the velocities will stay the same, and they will always be along the line of impact.
Okay, thank you.
Someone else had a question as well?
Yes, I did.
Yes.
I get that there is no impulse because, well, A and B are going in the same direction and the velocity of A is greater than B. That makes sense. What would happen if B was going in the opposite direction, however, the velocity of A was still greater than B?
You would have another condition. You will have, your linear momentum would still be conserved, but when you conserve it, you have to take care of the signs, right? So it would basically just become MVA minus MVB, and then after impact, if you're doing the analysis and you don't know where it's happened, you have to treat them as unknowns, and then it can just be equal to MA VA prime plus MA VB prime, assuming that both of the velocities are positive. Then also looking at your coefficient of restitution, which will be given to you, right? The two unknowns that you'll have are always going to be VA prime and VB prime, right? The initial conditions will be given to you. So you need two expressions. So you conserve your linear momentum to get one expression, and then hopefully you'll also be given the coefficient of restitution, because otherwise, you can't use conservation of energy to find out what the post-collision things are. And this will give you the second expression that you need.
Oh, I see.
All right, but you're right. You do have to account for the signs before. If they're moving in different directions, right, your expression would look different. Right now, since they're moving in the same direction, your linear momentum expression would look like MA VA plus MB VB is equal to MA VA prime plus MB VB prime, right? And here the reason for this plus is because they're both moving in the positive x direction. But if this was moving if VB was moving that way, this would be a minus direction, right? But this expression would still remain the same because these are still unknown, right? And when you're solving for unknowns, always assume they're in the positive direction. Whatever your answer comes out to be, you can fix with that later on, right? I hope I answered your question. Didn't meander.
Yes, sir. Now it makes sense now.
All right. So we're looking at that coefficient of restitution, just writing it out again, it was VB prime minus VA prime divided by VA minus VB, like that, right? And remember, this is your relative velocity after the collision. This is your relative velocity before the collision. All right. Now, the interesting things to note are that when you have this coefficient of restitution equals to 1, what does that mean?
Does that mean there's conservation
That's
of momentum?
They not just no momentum is always conserved along the line of impact, but it means conservation of energy. It means that it's a perfectly elastic impact. So it means perfectly, yeah, linear momentum along the line of impact is always conserved, even if energy is lost, because there's no impulse, right? Perfectly elastic impact, right? And what that means is that the total energy is conserved, right? And remember, again, just to reiterate this fact, this is only true when E is equal to 1. If E is equal to 0, that means everything, it's a perfectly plastic impact, right? Maybe they start moving in opposite directions with the same velocity. Oh, E is the coefficient of restitution. It's the quantity that is quantifying the bounciness, the energy that's lost when an impact takes place, right? So when you have something which impact each other, you might have some energy which gets lost to the surroundings, and you can't use your conservation of energy anymore. It's basically the bounciness that's being quantified. So that's what coefficient of restitution is. So this is perfectly plastic impact, right? And that means that a lot of your energy has gotten lost. All right. So this was when you have direct central impact along the line of your impact, everything, the movement that's happening. All right. Okay. So next, let's take a look at oblique central impact. Right. So what you have now we're not assuming those ideal conditions where those balls were so far apart. It becomes difficult to do that. So right before impact, that's a perfect circle, and don't mind my terrible drawing. That's my line of impact, right? And then you have the tangent, which is basically the tangential to the two surfaces where you meet, right? This is your normal direction. This is your tangential direction, like that, right? So this is the condition just before impact. Right? So you have, let's say, in some random direction, you have the body A that moves like that, and then this one comes in at another direction like that, right? So you have MB times VB, like that. Now, what happens is that after the impact, you will have 4 unknowns. Why will you have 4 unknowns? So before impact, all the conditions are known. We just know they're at different angles and they're not along the line of impact, right? After the impact, you'll have 4 unknowns for your velocity. Why is that the case, guys?
Because of
Yeah,
the
like 2 components per each
Because
velocity.
they go in the x and y components.
Because both the magnitude and the direction of your velocities are going to be unknown. So velocity and direction for ball A and velocity and direction for ball B. Or, as you guys said, you can think of it as the different components. So the components in the t direction and the components in the n direction. Essentially, it's saying the same thing. But you have 4 unknowns that you need to solve for. And that means that you need 4 expressions that you need to figure out to solve for, right? So let's get into it. Is that clear to everyone? Is that no means yes kind of thing? Right?
So,
Yes.
In the direct central impact, we didn't include mass of these balls. Is that because we assume that they're the same weight, or?
No, you can include it. That's a good point. You should include it. Mass remains the same. Mass remains the same. You're absolutely right. You should include it. It's just that it doesn't come into the coefficient side of things, so I didn't write it out. But all right, Mr. Rushford, you make a good point. You should include it, and you must write your expression out as well, which is basically your second equation, which is going to be MA VA plus MB VB is going to equal MA VA prime plus MB times VB prime, right? And you have to take note of the directions that you're using. The reason that I didn't write that expression was exactly because of the point that Mr. Mucella brought up, which was what if it's in the opposite direction? Then you have to be careful of your signs. All right.
Yes, thanks.
Right. So now, wow. See, this is what happens when you. Those were not circular at all. All right. Let's try again. 1 and 2. All right. For all intents and purposes, they're in the same direction, guys. Terrible, terrible drawing. But anyways, like that, right? You've got your line of impact, and then you've got the perpendicular line. Let's see, that's in the tangential direction like that. And then after impact, what's happening is we don't know what's happening, right? So you'll have, let's say, MA VA prime like that, and then MB VB prime like that, right? And there's 4 unknowns here because you don't know the magnitude and the direction, right? So this is after impact. Right? So the final velocities are unknown in magnitude and direction, right? So what that means is you have 4 unknowns. You need 4 expressions. Two expressions drop out really easily by just conserving the momentum of the body along the perpendicular direction to the line of impact, right? Because there's no impact that's happening here. Momentum should remain conserved. What that ends up meaning is that the tangential components of the velocities before and after impact remain the same. So you get the expression that the expressions rather have the tangential components for each particle right? What that means is that if I'm taking my component of VA in this tangential direction and of this VA prime in this tangential direction, they remain the same, right? So you need 4 expressions, right? So you get that VA in your tangential direction is equal to VA prime in your tangential direction. And similarly, VB in your tangential direction is equal to VB prime in your tangential direction. All right, so that gives you 2 expressions. We need 2 more, right? Linear momentum along the line of impact remains conserved. All right, and again, this is because of the fact that there's along the line of impact, there's no impulse, right? So that gives you your third expression, right? So let's number them. So this is 1, this is 2, right? So along this line of impact or this normal direction that you define, the momentum is conserved. And it's the total linear momentum, so the whole system.
Quick question.
Yes, please.
For the linear momentum, what's our R, the distance? Is it the 2 radius or the 2 diameters?
Doesn't matter. Why does that matter?
So if I'm not mistaken, linear momentum is R cross product MV, right?
That's angular momentum.
Oh,
Good question. That was angular momentum, not linear momentum. Not looking at angular momentum right now.
so what's the formula for linear momentum?
MV.
Oh, okay.
The moment of the linear momentum is angular momentum. That's what you're thinking of.
Oh, okay. Thanks.
Yep. So again, writing out everything in scalar form, I have MA times my VA in that along the line of impact, along the normal direction, plus MB times my VB in that along the normal direction is equal to MA times the A prime, the component that I have in the normal direction, plus MB times VB prime in my normal direction, right? And that gives me my third expression. I still need one more. And that comes from either you do conservation of energy when you're looking at a perfectly elastic impact, or the problem will tell you what the coefficient of restitution is. And that's going to be your fourth expression. All right, so let me write the fourth expression over here, right? So the normal components of the relative velocities are related by my coefficient of restitution, or E, COR, or E, like that, right? So my E is basically going to be VB prime normal times VA prime in the normal direction divided by VA, the normal, minus VB in your normal. And this is your fourth expression. Or if the, and I'm not writing this down, but take note, you guys. All right, you know what? Just write it down. Or conserve energy if collision is elastic. All right, and that'll give you your fourth expression. Well, technically it should say perfectly elastic, but you guys get the point. And if your coefficient of restitution is not given, in your problem, and you need a fourth expression, if you assume that energy is conserved, that's okay. That's the way to go. All right, guys, questions? No?
Oh, yeah, just real
Yeah.
quick. So when looking at equations 1 and 2 that you had set up, so velocity and then so VA and then VA prime are equal to each other, but we're talking about magnitude.
Just the magnitude in this tangential direction to the impact that happens. Yes.
Okay.
So you're basically taking the components of the velocities in the t and in the normal direction, right? And that gives you the 4 unknowns, because that's another way of writing velocity and direction, right? It's the 2 components.
Right. Okay. Just want to make sure. Thank you.
Yep. All right. Now, as you guys were talking about earlier today, we're done with the theory for kinetics. But now it's like, oh, when do I use what, right? So that's just comes from practice. But hint, when you're talking about forces, accelerations, use Newton's second law. When you're talking about one body, energy conservation, looking at velocities, looking at potential energy, you're looking at energy conservation. And when you're looking at bodies hitting each other, potentially looking at the velocities after that, then you're looking at impulse and momentum. But there's no like handbook, right? You could use different approaches to solve the same problem, and that's okay as well. So with that, what I wanted to summarize was the fact that you could have problems involving multiple principles, right? Because with kinetics, we've looked at 3 different things. Right? You've looked at Newton's second law. You've looked at the method of work and energy. Right? And now you've looked at impulse and momentum. Right? And the trick is, how do you figure out what you're going to do, right? Read the problem, and your problem will tell you what's the best way of solving it. There could be multiple ways to solve the same problem. All right.